And go ahead and get started here. Hopefully we'll have a few more people coming in. Welcome to the last week of classes, everyone, for the spring. The highlight of the last week of classes for me is always being able to introduce our amazing seniors and celebrate their capstones as they're graduating and going off to grad school or industry or wherever they're going. And so today is no different. Today I'm here to introduce our seniors, and we have 7 presentations today and another 7 tomorrow at noon here in the Planetarium. Thank you to Eric for hosting. First off today, in a short talk, we have Yuka Lin, and she is going to be talking to us about the nonlinear noise subtraction for low frequency that she's been working on with Dr. Zanelin for her Capstone project.
Okay, can you guys hear me? Awesome. Okay, so I guess to start off as like a brief background on my project, as to like why I even did this. So as most of you guys probably already know, Dr. Zanelin's research group here is essentially studying like the gravitational wave emissions from core collapse supernovae. So this is basically when a massive star reaches the end of its lifespan and experiences rapid collapse. In particular, we want to find the gravitational wave memory, which is going to be found in like the low frequency range of that signal. And usually these emissions can peak below, I believe, 10 hertz. Sorry. Okay. So essentially the goal is to come up with some noise reduction techniques that can help us find this low frequency signal that will get lost within that noise floor. So the nonsense algorithm was actually created fairly recently, about 2 to 3 years ago, by Dr. Gabriel Vallente over at Caltech. This stands for non-stationary estimation of noise subtraction and has been successfully applied to subtract noises from signals over 10 hertz. So my project was therefore to take that same algorithm and and sort of like modify it to see if it was possible to apply this to a lower frequency range below 10 hertz. Okay, so the purpose of this algorithm is to find the best parameters that can reduce the maximum amount of noise from the target strain if possible. The algorithm will then perform a prediction of the most optimal subtraction possible. Here, the equation that's being shown at the top basically models the strain signal that we want to subtract from. The first term, HGW, is the actual gravitational wave signal that we want to find. The rest of the terms are basically the noises that comes into a strain, and we want to be able to get rid of them. We can't do much about that last term over there, epsilon f, which are like fundamental noises. But in this algorithm that I was using, it basically will try to predict the best subtraction of the linear and nonlinear noise couplings. Noise couplings, just as a definition, they're just like the physical process of adding noise sources into the gravitational wave output. I guess to explain a little more, the main difference between the linear and nonlinear noise couplings is shown in the equation here too. With the linear, the noise is affected or witnessed by some auxiliary channel that couples into the strain. With the nonlinear case though, the noise coupling is modulated, so the effects of the noise contains non-stationary elements or effects, characteristics. Therefore, unlike the linear, we will need to utilize both the fast and slow modulation witness sources, as shown by x of t and s of t in the equation, in order to do the subtraction. And to explain, the auxiliary channels are like the time series data that is recorded by the actual detectors themselves, and these monitor like the detector behavior and environment. So let's just like jump right into results, and I'm gonna explain in the order of how I decided to approach this project, because this was like in several steps. So first of all, there's like many auxiliary channels in the LIGO system to look at. So in order to go through all of those, there needs to be a systematic way to at least narrow down the most relevant signals. The first step is basically making sure that there is linear coherence between the original target strain and auxiliary channel. This means checking if two channels have any correlation between them. So if there's absolutely like no correlation at all, then there's no point in trying to perform any subtractions. Over here, I just put this graph as one example. You can see that there's quite a bit of coherence above the red line, below 10 hertz. All right, so step 2. So now once we've gone through and we see like what channels are the most relevant, we can start by doing the subtraction for the linear first. The good thing with the linear subtraction is that it's a lot easier to systematically pick out channels, because we simply just had to go through the process that I explained in the previous slide and just go based off that. And you could just, yeah, and then you could just like plug those parameters into the algorithm and see if it actually does like a lot of subtraction. And then also on the slide, I know like the channel names are kind of weird, so I kind of put like a name convention. Sorry. Okay, so I'm just gonna jump into the actual results slide where we have the subtractions happening. The red line is the target strain that we want to subtract from. The yellow-orange line is like the linear subtraction happening, and then the blue line is the nonlinear subtraction. So I want to draw attention to the bottom graph because it makes it a lot easier to see the differences in subtraction. So over here, you can see that between 1 to 4 hertz, we get some improvement with the nonlinear subtraction. But over in like the 6 to 10 hertz range, we get like, it ends up worsening. So I just want to point out that this algorithm doesn't always converge, so we cannot get the most optimal subtraction all the time. So as a conclusion, I figure out that we basically just need to explore more of the auxiliary channels that we want to subtract from. And essentially, over the years, the LIGO detectors will improve and will improve its capabilities. So then we might be able to get more subtraction then. I just want to give a quick acknowledgement to Dr. Valiente for helping me for being my mentor when at my REU last summer, and also for teaching me how to use the code, and of course Dr. Zanolin for being my mentor for the last year or so. So yeah, that concludes my presentation. Are there any questions?
All right, thank you, Yuka. We'll have time for one question, but while we do that, can I ask Daniel, Austin, and Lauren to start setting up their talk? All right, Dr. Bailey.
I had a question on the equation. Hi, do you still have your slides up? Can you go to the equation? I'm a theorist, so I like equations. The linear term, nonlinear. So when you say nonlinear, in what variable there is it nonlinear? Like I would expect to see xi squared or s squared or cubed or something. Or am I not?
With the nonlinear, however, the signals are modulated, so it's modulated into the noise coupling. So that's in a sense what makes that one more nonlinear, non-stationary.
All right, thanks again, Yuka. All right, next up we have a group presentation, so they get a little more time. And we are going to learn about nuclear thermal propulsion. In particular, we have Lauren Bryan. Wave hello. All right, Daniel Cunningham, Brady O'Hare, and Austin Weber. All will be working on this together, and they were advised, I believe, by Dr. Smith. So thank you very much. You guys get 20 minutes.
So today we're going to be discussing our work over the past year, working on nuclear thermal propulsion for rocket engines, and specifically our work with the JON4 particle sim. It is. Sorry, the clicker's not working. It's not working. Whoops, hold on. Yeah, it's not.
Oh, so yeah, it needs to be in.
Hey, there we go. Okay, so as a brief overview of everything that we're going to be discussing, we're going to be going over what a nuclear thermal propulsion engine is, what our goal for the project was, the mission requirements that we had set forth, looking at some historical designs that have been done in the past, further research looking in the modern era, our initial design for our engine, and then kind of going through that design process to improve our engine design, the JM4 simulation that we used, and then capping it off with the successes, challenges, and next steps for the project moving forward. So, nuclear thermal propulsion, often abbreviated to NTP, is where instead of a traditional chemical rocket where we have combustion giving us our thrust, we are using a nuclear core, and we're using the heat expelled from nuclear fission in order to heat some sort of propellant that we pass through our system. And the core to this is using highly enriched neutron sources and some sort of neutron reflector to continue this fission process as long as we need. All stored within some sort of metal structure. The propellant is typically hydrogen, but can really be any gas or even a liquid. And really the main draw of nuclear thermal propulsion is the high specific impulse and the extremely long lifespan of the nuclear core. But with that is the need for large propellant reserves to match that long lifespan. So I'm going to hand it off to Brady real quick.
So for this project, we need to have a goal in mind when designing an engine like this. You need to be able to apply values and stuff like that, what your range of ISP and thrust looks like. So for the goal of the project, we decided to go with a modular NTP engine design that is capable of a mission to Mars. The reason that we picked this mission to Mars was because NASA's design reference architecture has everything laid out for this, and this is something that NASA is already investing in into companies with NTP engines. And so the idea was to optimize a new NTP engine core design that has not been historically attempted, and we'll kind of go through that in a bit. And so going forward, we had to define some mission requirements. These are necessary in order to design an engine itself. If you don't have these values, you really have no starting point. So the main one that Riley already mentioned was that the specific impulse is very high compared to chemical rockets. In things like the Saturn V, you only get around 300 to 400 seconds of specific impulse, whereas in nuclear thermal propulsion, you can get 875 to, I've seen upwards of 1,000, and it still produces a reasonable amount of thrust as opposed to like an electrical engine where you do have that high ISP, but you only produce thrust of like a kilonewton at max. And then you can see that these are some other design reference requirements that we need in order to continue with that design. And so I'll pass it back to Riley to talk about historical design.
So at the beginning of the project, we decided to look at previous efforts, and the main thing that we found was the NERVA project that was done in the 1960s. That project focused on two different type of core designs, a tungsten ceramet and a graphite substrate. A ceramet is a mix of a metal and a ceramic, so they would use a metal, typically tungsten, and then mix that with a ceramic that contained their nuclear material. And then had channels for the propellant to pass through. And a graphite substrate was just a graphite structure that had pockets of nuclear material spread within. The biggest kind of drawback from pursuing these sorts of designs was that they had to come up with entirely new manufacturing processes in order to get the durability and resistance to the high temperatures that they were looking for. Additionally, they used a boron as a neutron reflector, and that was to reflect all of the neutrons back into the core to continue this fission process to repeat over and over and over again to get more thermal output. And then additionally, they would use beryllium control drums, and the purpose of those is to absorb neutrons. So if our engine was getting too hot, we would be able to turn these drums to absorb some of those neutrons to kind of slow down the fission process. They also had to use turbopumps in order to shoot a hydrogen propellant through the nuclear core, that to be able to propel the hydrogen to get the thrust that they were needing. Additionally, they would use zirconium hydride as a moderator inside of tie tubes within the core itself. There's just another level of neutron moderation to keep things from getting out of hand. And then they also use zirconium carbide to line all of their propellant channels to resist the high flow rate and high temperatures of the propellant that would break down the metal core that the propellant would be passing through. And lastly, they used a honeycomb layout, as you can kind of see on the image on the right. Used this repeated honeycomb layout to be able to expand this engine to any size that they had needed. So there are current modern efforts. NASA currently has a contract out to develop an entirely brand new NTP engine. And the main bits of information that we were able to gather is that it's following directly in the footsteps that were set forth by NERVA. Instead of pure tungsten, they were using a tungsten molybdenum alloy, and that they were using 19.75% enriched U-235. However, the exact method of how this nuclear fuel was being implemented in the engine is not well known. And kind of as I say up here, many of the details are proprietary since this is a current contract that NASA has put forth. So, in addition to kind of the efforts that are in the industry space, we decided to look at other types of nuclear cores, as well as looking at other types of propellants. We were able to find some information that was tests that were conducted by NASA, looking at nitrogen, carbon dioxide, methane, ammonium, and water, in addition to hydrogen. And ultimately, what we had landed on was, I'll hand this over to Brady.
So as Riley was saying, we ended up landing on this initial design, which is a hybrid between a traditional nuclear reactor with the honeycomb design that we saw in the NERVA slides earlier. And so basically the way that this works is those gray dots are where our fuel pins would be, and the black dots are central channels for propellant. And so this would be made of that molybdenum tungsten alloy that Riley mentioned earlier with the BWXT engine that NASA is funding. And so the idea is to continue to use that hexagonal core to maintain that modularity that we talked about earlier. And so modularity can come in one of two ways. It can either come in the individual hexagon shapes that we have, or it can come in the honeycomb shape of the 7, and then that way these can be produced in a manner that's much more efficient, and we can add more and more of these modules, whether it be the first one that I mentioned or the latter one that I mentioned, thus making an engine big enough to support different mission types.
So, continuing kind of at more outside of the engine core, we decided to look at beryllium oxide for our control drums, and continuing to use boron as a neutron reflector. The move to beryllium oxide was we were able to find some papers that showed that they had, in terms of being a neutron absorber, it had a much higher cross-sectional area with respect to just pure beryllium. We decided to also continue with a zirconium carbide lining, and that was just due to the successes from the NERVA project. We decided to ultimately go with hydrogen as our propellant, and the main driving force behind this is it is the most well explored, and it is what is currently being pursued by current contractors for NASA. And so with this, the entire engine is an iterative design process where it is slowly refined over testing to change small variables in order to get more optimal heat output. So I'm going to hand it on over to Austin to talk about that.
So our iterative design process starts with CATIA. Now, if you're familiar with Geant, you know you can build things in Geant itself, but you can't build hexagonal shapes very easily, so that is where CATIA comes into play. Next, we pass on the CAD file into Geant 4, and that has our reactor geometry. And then Geant 4 is the Monte Carlo simulator that does all the physics processes and actually tracks our neutrons for us. Then once we get the data from our neutrons, we pass that to ANSYS to do the fluid dynamics and heat transfer, since that is also another limitation of Geant 4. And then at the end, we optimize and run through the steps and make our reactor better as we go on. So Geant 4, the objectives. We need to track the neutron particles, since that is the main thing for fissioning of uranium-235. They each get a unique ID. We get their position in XYZ coordinates, and we get where their energy is deposited to and how much energy that is, which is very crucial for the heat in ANSYS. In addition, we had to add additional libraries to Geant 4 to turn them on, and that is our specific neutron fissioning process and the time dependency. And then we also needed to optimize our nuclear reactor in Geant. Now from this diagram, you can see Geant 4 is kind of a beast, but we'll start with CATIA since that's our first step. Basically just build the CAD file, send it to Geant. Now in order to get Geant to run and build properly, you need to first install Visual Studios, because Geant 4 is coded in C++. CMake makes it easier to build Geant 4, and then Qt and OpenGL are also necessary to get the beautiful graphics I will show you later. All of this goes hand in hand, and about 2 hours later after you build it, you get to see if it works or not. Unfortunately, it took us about 4 months to get it to fully work, just because of how long you have to sit at your computer just waiting for the download and build to do. And then you get to the simulation part, and that's where you have to code all of this in C++. After that, Geant 4 likes to output all of its files into root and doesn't like to do anything else. So we also had to get root to review our data and get a little bit of histograms on that, so then we could send it into ANSYS. Right. On your left is actually one run of our code for Geant 4. You can see all the green lines and the little yellow dots in the middle there. Each one of those yellow dots is a neutron interaction point, and each green line is the track of a neutron. Now, This is not all the neutrons since you can only render 50,000 of them, but that's a pretty good number for us. On to the right side is the actual more basic detector geometry we have. It's the tungsten molybdenum on the outside of this like cyan color, and then in the very middle, a little bit hard to see, but that is our uranium dioxide core of the 19.75% of uranium-235. So in order to get our data for the XYZ coordinates of the neutrons, we have to build a sensitive detector. As you can see over here, that's another run of our GEONT, which starts with just one neutron to get the fissioning process started, and the whole white box around it are the sensitive detectors. Now there's 64,000 little detectors there that are each an inch cubed, and that takes up a lot of time and processing power on your computer to run all of this. But on the middle, you can see a little bit more of the geometry and how it encompasses all the sensitive detectors. And same with this one. This is a cross-sectional map. A little bit hard to see in here, though. Now, this is our really cool picture on the left there. It's a little bit more fleshed out mesh of the tungsten molybdenum, which is the blue, and the uranium core on the inside. And this is just another run of the GEONT4 program. And what is actually happening is the fissioning of uranium-235. Now, our reactor runs very neutron-rich, which gives us beta decay, also some extra neutrons, and daughter nuclei that come off of that since it is so neutron-rich. Now I'll hand it over to Lauren to talk about which fissioning model we actually chose for our program.
So for here we had to decide how we wanted to do the hydronic physics. So we started with our basics physics list. We decided on doing the quark gluon string model. From there we decided to get our byproducts what kind of model we needed, and we landed on the Bertini cascade model. And then from there we added that neutron high precision package. This lets us see the neutrons below 20 mega electron volts to get down to those thermal energies. And so for our success so far, so we got GEONT4 to properly install. It was not easy, but we managed to do it within 4 months. And then from there, we were able to build a simple detector construction. Again, we can't get those hexagonal prisms yet without CAD, so we just built those cylinders for now. And then we added the sensitive detectors to it to detect our energy deposits and any other properties we wanted. And then from there, again, we added that header file to get the proper nuclear fission we needed. And then just recently, we got CAD to go into GEONT4 and input or import a mesh file. And so soon we'll be able to get those hexagonal prisms and hopefully our full reactor in there. So along the way, we definitely had some challenges and some lessons learned, again, with installing GEONT4. In hindsight, we realized later on that Linux would have been better than Windows just because you can do partitions and multi-threading, and that would help us with a challenge we had later on. Again, with integrating those cross-platform softwares, that took some time, and it came down to minuscule details. So just missing one thing after running it for 40 minutes, you're missing one thing, it doesn't work, you had to start from scratch. You had to delete it, you had to do it again, and some of the manuals were missing key aspects. So we kind of had to debug and figure out what those were. And then moving on, once GEONT4 is running, GEONT4 is approximately 1 million lines of code, and it has its own syntax. It's a little bit different from C++. It has its own wording, so you kind of got to figure that out. And then it has multiple libraries, so deciding what libraries we needed, which ones we didn't. And then it comes down to the runtime. Currently, with our 64,000 sensitive detectors, we're running into the issue where our computers can't handle the memory or the time. Sometimes it takes too long and it just crashes. And other times it just takes like 40 minutes to run. And so that is also the diagrams we showed you. That was before time dependency. We haven't added that in. So once we add that in, our computers are going to have some serious issues, and we might have to move up to a supercomputer to handle that. And then lastly, again, the geometry we can't do hexagonal prisms. They're not a predefined geometric shape in Jant4, which is why we need to input those CATIA files to get our actual nuclear reactor design. And then for the next stages, now that we have those sensitive detectors, we're working on producing those histograms and those new tuples and reading them out en route. We're close, but we're not there yet. We still have a few errors in our code. And then after that, we're going to add in the time dependency, and from there, start putting in the complete reactor into Jant4 and continuing that iterative process to optimize. And then we would like to say thank you to Dr. Smith and Dr. White and the rest of the NERV team that's not here today for all their help. We couldn't have made it this far without them. And while we haven't accomplished as much as we wanted to within the year, we're happy with making it through the challenges we did, and we feel that we have laid a good foundation base for the next people to come in. So if anyone wants to join, please let us know or Dr. Smith know, because we are all seniors. And with that, thank you.
Thank you so much. We have time for a couple questions here as the next team gets set up. So they had a long presentation. Let's give them a few questions. Anyone besides Dr. Bailey today? He wants more equations.
Can you go back to the slide that had the numbers for the rockets at the beginning? The thrust and so on. It was way in the beginning. Yeah, so I was looking at this and I was wondering, it seems like the numbers here, the delta V and the thrust are small compared to the best current chemical rockets we have. Is there a reason that
Yes.
we're not
So I guess I forgot to mention, but the nuclear thermal propulsion system that we have proposed would be used as only as an in-space propulsion method. And so it would be superior to chemical rockets due to the longevity of the nuclear engine itself. So while it doesn't have nearly the same thrust as, say, a launch vehicle like the SLS or something like that, the ISP to thrust ratio that we have and the longevity of the lifespan, as well as the you don't need to carry as much propellant with you for missions to Mars as you would as a chemical rocket. It is the superior system as opposed to using a chemical rocket to transport yourself to Mars.
The other point I would make with that is that you can't launch this from the surface of the Earth. And,
Yeah.
and so it's, you have to assemble it out in space because we have treaties that we have to honor. And so that's why that helps in the delta V and the whole performance characteristics that you've outlined there. Yeah.
Any other questions today? Well, let's. Oh, missed one.
Just curious if you're familiar with the Orion Project.
I am indeed familiar with the Orion Project. The issue with the Orion Project is exactly as Dr. Smith said, where you would essentially kill the planet in order to make it off the planet. That's kind of like a last ditch effort to get off.
We got one more in the back, but the next team can start setting up.
So when you're doing a NERVA rocket, or what you're doing here, what is the volume of hydrogen required through the tube per second to produce the 112 kilonewtons of thrust, and how does that compare to, say, an ion engine and the volume of xenon?
So if you took the values that were put up there in the requirements for the thrust and the ISP, you could actually calculate a mass flow rate that you would need of hydrogen through the engine in order to achieve those values. I think with those values, it comes out to around 12.5 kilograms per second. In chemical rockets, you're going to have much larger amounts of propellant and oxidizer as well in order to achieve the levels of thrust that you see with traditional rockets today.
All right, thank you. All right, our next presentation is again a joint presentation from Jeremy Gordon and Jonah Greenwood. And they have also been working with Dr. Smith, and they are going to be talking about a moose.
Alrighty, so good afternoon, everyone. I'm Jonah Greenwood.
And I'm Jeremy Gordon.
And as said, we're going to be talking about moose today. So just you can see, we are in fact talking about moose. But no, we'll explain what moose is later on, just an acronym, don't worry about it. But yes, we are continuing on the presentation that was just given with the NERVA project. We're just a separate branch of what everyone else has been doing with the JAON. We're going to be using a different software called Moose. So our objectives are that we wanted to find a new software. As you heard, there were a lot of problems within the JAON stuff going on. It took almost a full semester just to get things off the ground and up and running. So around the beginning of February, Jeremy decided he was going to look for new software that would be able to model all of these nuclear fissions as well as heat flow a little bit more efficiently than JAON. So that's what we set out to do. And then continuing with JAON, we wanted to continue with the mesh grid like they described in their last presentation. And then we just wanted to model heat flow through that. So we're not actually going to be doing much fissioning in this actual software itself. We'll talk about that at the very end of the presentation, but this is more for the heat flow of the actual energy that has been produced by that nuclear core. Moose. So what is moose? I know you're all done waiting. We've been talking a lot about moose. As you can see, not the animal, it's the software down at the bottom. This software was developed by Idaho National Laboratory, and it stands for the Multi-Physics Object-Oriented Simulation Environment, MOOSE. A really funny anecdote is that they actually spent like 3 full days trying to make up this acronym so they could get it to spell out moose because all of their software is based off of animal names. Really weird, but really cool. But yeah, what we'll be using this for is just to utilize different mesh problems for how heat will flow through different materials given an initial temperature, and then just how it will travel through that material as time flows on. Moose.
All right, so as Jonah kind of hinted on, some of the uses for moose that we're using right now is to use it to model the heat transfer. We talk about later on, Jonah took some time to do some hand calculations to figure out how much heat a 1 kilogram rod of 20% enriched, or about 20% enriched uranium-235 will produce per unit time, and we've been able to convert that into a temperature where we're able to then see that diffuse into our meshes that we can use to model the engines. Another example that I will pull up, you might need to pull that up. One high-level example that Idaho National Labs actually has together here is showing what if a little chip of, let me use my, this fuel pellet was fractured off during shipping or during something, what kind of effects that would have within the reactor. And I'll play this real quick to give you an idea of what a very high-level simulation can do.
What we're looking at is a piece of a pellet here has chipped away, either due to some manufacturing defect or maybe while it was in transport, but a piece of the pellet is missing, which you can see on the middle pellet there on the left, and it's going to cause a high stress state in the cladding in that same area just due to that missing surface there. So you can see the pellets warm up and then they densify. Then later on, the pellets actually swell back out, because there's fission products building up inside of them, and then they'll run into the protective coating, the cladding, and you can see the high stress state build. What we're looking at is a piece of...
So it just loops there, but what that shows is we don't have to build in any time dependencies. Time dependencies are built within Moose, so that we are able to do stuff on order of a year. That was going out to well over a year that simulation was running, and it is able to run that simulation a little bit easier as this code has been made a little bit more modern compared to Geant 4. I believe Geant 4 it was created in 1998, so almost 25 years. And it has been tested, and it has been used to simulate these exact things before. But what Joan and I have set out to do is try and find a newer program that might be able to do it even better.
Alrighty, so Giant crew, stick with me here. Gonna roast you guys a little bit, okay? But no, seriously, the main reason we decided to switch the software was, as you heard, it took them like 4.5 months to download Geant. We figured if this project is going to continue, it might be more beneficial for people coming in to have software that doesn't take that long to download and set up and install properly. Jeremy will talk about that in just a second. You'll see that it's much, much less time to get that working properly. Some other reasons that we wanted to switch software was that there were 5 of us currently working on the Geant software, and that whenever we would encounter a problem, all 5 of us would be working on it individually, and once of us got it, we would share our code with the other 4, and they would have to scrap everything they did and use that code. That got very frustrating because all of that time and effort you put into was just scrapped at the end because one person figured it out like maybe 5 minutes before you did. But it's very important that everyone has the same code working on it, just because you don't want to have several different projects running and then at the end have some sort of factor that's different between it that was just one thing you didn't communicate well enough instead of just switching to the other code. So Jeremy and I decided it'd be more beneficial for the 2 of us to split off and start working more on the heat flow through the material rather than the actual fissioning process of the core. So yeah.
All right, and one thing also on there is when we started to branch off, we weren't sure if Moose would actually be able to do the fissioning process that we were wanting, if it was able to accomplish everything just based on the preliminary examples that we had. And upon looking through Idaho National Lab's website, I came across Moose and some of its other packages that we'll talk about a little bit later on that were specifically designed for, there is one that actually has been used to simulate nuclear thermal propulsion in the past. But as Jonah said, this is much more user-friendly than Geant. Instead of installing 3 different programs to then have one of those programs install Geant for you, you just have to follow their lovely install guide. This is actually just a screenshot from their website. There is a lot of documentation on getting it up and running. The only drawback is that it does require Linux, either a virtual machine or a Linux partition, which I found was easier to operate in. And when you're going through the whole process, they have literally line for line what you need to put in, what things you need to change for your system, and they actually have a like, hey, are you getting this error? You might need to change this, which was a very pleasant change from the install process with Geant. And the other nice thing with this is it has its own built-in GUI. It's called Peacock. They really love naming things after animals. And you'll see what that GUI looks like on some of the following slides here.
So one thing Jeremy did forget to mention is that install time took maybe 30 minutes as opposed to 4 months, so a little bit faster, not much. So building from Geant, like we have mentioned before, we spent the entire first semester working with Geant. We worked on the project, so we already knew exactly what the system requirements was, what the Geant crew was trying to do. So then we could just implement all of that into Moose and Peacock itself. So we already knew what the core was going to look like. We knew the hexagonal pattern with the 6 holes and then the 1 larger hydrogen hole. We knew what all the materials were with the uranium dioxide enriched to 19.75 U-235, on that core. We knew the tungsten molybdenum alloy, so we could implement all of that right into Moose right away. We didn't have to mess around, figure out what the best materials were going to be. We could just hit the ground running, immediately implement that, see how the heat would flow through it, assuming we put the temperature at those nuclear rods. So yeah, we hit the ground running. We were able to get going right away. It was really nice.
Okay, so up here are two examples from that come with the install of Moose, showing kind of what Moose is capable of. The one on your right, my left, is showing convected heat through, they have it called their reactor mesh, which seems to be a portion of a much larger mesh. But there is, where that blue ring is, a emptied out region, and you can see how the heat flows through it, as well as on the other example over here. It is diffusion instead of convection, and you can see how heat is traveling through the mesh differently. Then, another moose. Some more of these examples. You can go through and refine the mesh throughout Moose itself. So this is kind of showing an example of, it is kind of hard to see. It's easier to see on this one. Down here, the mesh is less defined, and up around the other parts, it can be more defined for more accurate measurements. Again, this is a different diffusion versus convection. And this actually leads into another moose. Kind of our most working model. We've had a couple issues as far as getting Moose up and running. I know we talk about it like it's some wonderful program. There are still plenty of issues that we need to flesh out. One of them being Moose claims to accept a wide variety of meshes. Brady was very generous and provided one for us, so thank you a lot. Unfortunately, Moose seemed to think it was in 4 dimensions, and no matter how much I played with the code, it would not allow me to run it. So I decided to go with the mesh that you saw on the slide previous. And from some of Jonah's hand calculations, which he'll talk about a little bit later, we found that the heat produced would be about 4,000 degrees Kelvin. And if we just wanted to assume that it was just going to be sitting out in the vacuum of space at about 2.7 degrees Kelvin, how would this heat transport through our mesh? This isn't a flawless mesh. One of the areas where we ran into errors is, well, it looks like a very solid object here. Unfortunately, on the inside, it is hollow. So it does make kind of that heat transport very difficult to visualize and actually do, because there's no mesh connecting the outside wall to the inside wall where our heat is. But I think this image best shows what our goal of having Moose and what we were hoping to accomplish with this. If you imagine, this is one of the little gray dots on the last presentation that Brady showed. This is where a fuel rod would be, and it would be heating up the surrounding area. And in an ideal world where we have a better mesh, we would be seeing how it's heating up the core itself, what kind of temperatures is the hydrogen going to be exposed to, so we know what kind of temperatures to be expecting the hydrogen to be exiting at.
Alrighty, so we're basically caught up to where Jeremy and I are right now in the project. So now we're going to talk a little bit about future steps for everybody who's on the project and wants to continue using Moose. So the next biggest step is just finalizing that mesh. As Jeremy's talked about, it's been challenging to get the appropriate mesh we want in there. We want that hexagonal shape with 6 cores and 1 open larger cylinder in the middle for the hydrogen to flow through. So that'll be the next big step. And then once we get that, we can compare the temperature, or use the temperatures that we've calculated and have the heat flow through it as compared to our mission requirements for traveling to Mars. So throughout the semester, I went and did some just basic hand calculations to find the absolute like minimum values of the thermal power that would be produced by the engine. So for like a 120-day transit with a 1-month orbit, and this is assuming a constant burn of our core, we would have thermal power that could be as high as about 6.9 gigawatts. So a relatively average kind of engine size, but this is assuming constant burn. This is assuming you don't cut it during the orbit, which you would most likely do, just have it on a low energy mode. Assuming up to a 180-day transit in 1-month orbit, the thermal power would be as high as 4.9 gigawatts. Remember that this is the absolute minimum, and this is accounting for all of the energy that would be added to all the neutrons that happen during the fission process and all of the daughter particles that are produced. So this is all just thermal power that would then transfer through the core itself into that hydrogen tube, and then that would heat up the hydrogen, effectively acting as a propellant. Some more things that we want to do is finish that full-scale mock-up of just one single core with a hexagonal shape, and then adding more of those hexagonal cores together, like you saw earlier as Riley explained, with the 7 different hexagonal shapes, because that's the kind of design and shape of the engine that we'll actually be using, in theory, to go to Mars. So we'll want to consider how that'll change the heat, how it flows through it, considering we'll have more than one core burning at a time. And then the last thing we want to do is implement other softwares that's created by Idaho National Labs called Bison and Griffin. These were specifically created for nuclear fission, so that way we could almost eliminate the need of having to take data from the Giant crew. We could do it all in just the Moose software itself, because Moose is kind of the big, I guess, parent software for everything else that you can then add other softwares to, but it all just runs from Moose. So I'll hand this off to Jeremy so he can talk about these 2 softwares.
So ideally, we'd love to work with Idaho National Labs to use Bison and Griffin. Unfortunately, both of these required licenses, and at the time where we were switching over to Moose, it wasn't. We weren't in a spot where we could really try and gain a license this semester. In addition, a lot of the material that these programs have is export controlled. Meaning that it's stuff protected by the federal government. So that would be another, thing we'd have to overcome. So we would love to work with these. Griffin is the one that actually has been used to model nuclear thermal propulsion in the past. It is primarily looking at radiation transport as well. And Bison is a finite element-based nuclear fuel performance code. So it evaluates how good your fuel source is. So we took a lot of this information from Idaho National Lab, so definitely a large thanks to them. A big thank you to Dr. Smith for all the help he's provided this last year, and for me and Jonah the past 4 years. But with that, any questions?
We have time for maybe one question while Parker gets set up. So who has the question today for Jonah and Jeremy? Got one in the back.
So just as a clarification, so you're saying that you needed a specific kind of mesh, and your analysis does not look at what's going on inside of the mesh, but it just looks at what's going on the surface of the mesh?
Yes, yeah, the mesh that we currently have is a basically a cube, a hollow cube with a cylinder punched through it, and there's nothing connecting that cylinder to the walls of the cube. So in an ideal world, we'd like to have one that's connected throughout the center of it.
So what kind of simulation does it do? So you mentioned even on the last slide the finite element. What type of simulation is Moose actually doing?
So what we've been mainly using it for is thermal heat transport. We can put in what materials we would like, and we can see the way that heat is propagating through it. And then with some of the other packages, it would be ideal for us to actually have it do the fissioning and create the heat itself, so that we don't have to use hand calculations to get those values.
All right, let's thank Jonah and Jeremy again. Our last speaker today is Parker Landon, who is doing a dual degree here at Embry-Riddle. And so she's going to be talking with us today about quantizing the unseen.
All right, thank you, Dr. Richardson. So I'm going to be shifting a little bit away from Capstone. This is actually not my Capstone project and is actually my research project. I'd like a big thank you to Dr. Pavlina, who is my mentor on this project, as well as the Undergraduate Research Institute and Arizona Space Grant Committees for funding me in this project. So jumping right into it, this is actually a continuation of my previous work on controlling the unseen, or this is quantizing the unseen. So the project that I did previously was with Dr. Grederson, and we were working on modulating the output of a laser. We were taking the output and we were trying to squash down all of that noise that we had on that, all of that unnecessary signal that we did not want to see on our signal. So what we did was amplitude modulation, which is compressing and expanding our amplitude of our signal, as well as controlling the DC content, shifting it up and down. From this, we can see on this graph on the left-hand side, you can see a orange line. That is the signal laser without my controller wrapped around it. So you can actually see on the y-axis, we have magnitude in decibels, and on the x-axis, we have frequency in hertz. So as you can see, that orange line is actually much higher. It has a higher magnitude compared to my filtered signal, which is that blue line. So from this, we were able to decrease the low frequency noise on our laser, but while still keeping our high frequency content. So this is exactly what we want to see. So I keep throwing the word noise around, so let's kind of pin that down and describe that easier. So the system that we are working with can be thought of as a black box. We have our input, which is going to be power, and our output, which are going to be photons. So of course, in a perfect world, everything that we put in is going to be exactly what we put out. However, that is not the case. We do have some uncertainty on the input and uncertainty on the output. So the things that we may experience in the lab while we're collecting a very precise and accurate measurement, we might have someone walk into the lab, slam a door, and vibrate the entire optics table. So that would actually be shown on the output of our laser. On top of that, we may have thermal fluctuations where the air conditioner turned on and changed the room temperature. So these can be also considered as inputs to our system, where this results in an output of what we're calling noise. So what we want to do is remove that noise utilizing some of these techniques. And this project that I am focusing on is actually characterizing the thermal fluctuations, so those thermal noise. So what happens when we remove everything from the system? We have a perfect input and a perfect output. We have no uncertainty on the input, so therefore you would expect no uncertainty on the output. However, this is not the case. Our system itself has some form of uncertainty. We can call that a quantum probabilistic. It's very dependent on statistics. And this results in what we call quantum noise. So this is kind of the limitation. This is the limit of our entire system. So removing all of that uncertainty on the input will reach this threshold point called the quantum noise threshold. So this is the end goal of this project. We're going to characterize our diode laser, and we are going to be able to then reach that quantum threshold for it. So as you can see here, we have a plot here. As I had said, I am working with a diode laser, and I'm modeling it to begin this process of reaching that quantum threshold. So if any of you have heard of the Shockley diode equation, it's right here. We have on the y-axis is current, and on the x-axis is our voltage potential. So when we turn on the laser, you can see a huge spike of current that is going through, and that is what we see as a beam of light. Light and current are proportional to each other, so when we reach this turn-on point, when we flip on our laser, we're going to see a cascading of electrons. However, again, we do not live in the theoretical world, we live in the real world, and this is not a perfect model that represents everything. We actually need to expand this model in 3 dimensions to encompass the thermal dependency of this current. So say, for example, I have a really hot laser. That thermal energy is in addition to the voltage potential. So increasing that temperature is actually going to shift our turn-on point. So what exactly I did is I modeled this. I was able to get a nonlinear model, a nonlinear representation of this by expanding into 3 dimensions. We have current on the z-axis and voltage and temperature on the x and y axis. However, again, like I said, this is nonlinear, which is very difficult to utilize in control practices. So what I have done is I've taken Taylor expansions of this model, and you can see my model, and they are very visually similar. It's kind of difficult to pick out which is which, so I can quantize that by utilizing the percent difference between both of my models. So right here is the graph that tells us for each one of my models comparing the linear and nonlinear, we can find the percent difference between that. So on the y-axis, we have the percent difference, and then on the x-axis is the location of the temperature that we're working with. So as you can see here, we have about 2.5% of difference between my model and the nonlinear model at about 65 degrees Fahrenheit. So this is a good starting point and allows us to understand what temperatures will be most optimal using my model. So now that I have a model, it's time to experiment and test it. So we have here is a diode laser that has a temperature device attached to it. You can see this is the diode laser, and this is my temperature device. And we are utilizing a photodiode right here to watch as the temperature changes, watch the intensity change from that diode laser. So the first test that I did was looking primarily at the temperature over time. So as I turn on my laser, over time it's going to heat up. And as you can see here, we do not have an exact correlation between time, but time is proportional to current. So we actually can see that this curve falls right here, confirming my first part of my model. The second part is focusing on the change of voltage over the change of temperature. As you can see, is a linear relationship. And on my model, we have voltage and we have temperature. So this actually falls right here. So perfect, we have 2 examples that are confirming my model. Our experiments are following very closely to the model. And what next steps we need to do is we're going to expand at different temperature regions. So for example, we started at 65 degrees Fahrenheit. Well, then I can Taylor expand at different temperature ranges, parse those pieces together, and develop a solution space. If anyone has seen a state space vector, state space representation of our system, it is a solution space, the reactive space of your system. So for this model, we'll be using T for temperature and I for current, which are 2 orthogonal components of my state space. And then we're going to expand into 4 dimensions by looking at T dot, which is temperature over time, and I dot, which is current over time. So utilizing this 4-dimensional space, we can then start utilizing controls theory, where we can define the system in feedback. This allows us to use that modulation techniques, as I was talking about beforehand, and we can remove that temperature dependency. And great thing about this is that the steps that I've done here can be utilized for any diode laser. So everything that I'm characterizing here can be utilized by changing parameters slightly for your specific customizable laser. And this is what we would define as the characteristic polynomial, which allows us to give some extra wiggle room for that controls aspect. So just a review of what I've done. I've been able to model my laser. I then linearized that model, and then I experimentally confirmed that model was accurate. The next steps, of course, as I previously said, is expanding upon these models at different temperature regions, putting them together, and then utilize them in a controller state space environment and test that in MATLAB. So again, I'd like to give a big thank you to Dr. Richardson for inviting all of us and everyone coming here today. We really appreciate supporting us today. Are there any questions?
We have time for maybe one question today for Parker. Anyone?
Yeah, I'm going. I got it.
No, it's not a question on the presentation. It's just you said you also have a separate Capstone project?
This is one of 3 research projects that I'm currently a part of. And then my capstone project is part of the EagleSat team. We're developing a communication system for EagleSat 2. So I'm on the onboard computer focus of that.
And you're a double major?
Yes.
Are you sleeping?
No.
Oh, I'm sorry to hear that.
Well, let's thank all of our speakers again today. In addition to these wonderful talks we had today, we have 7 more capstone presentations tomorrow, same place, same time. And in addition to thanking them, I would also like to thank Dr. Ann Betcher, Director of Undergrad Research Institute, who came today. I know she has funded a lot of these students along their way with their research, and we just want to, as a department, thank you for your support. All right, everyone, have a great day.